Welcome back to Differential Calculus. In this video, I want to talk about continuous functions. You can see behind me I have this definition that we've talked about previously. A function is continuous if you can sketch the graph of the function without lifting your pen. And as I've said before, at the college algebra pre-calculus level, this kind of definition is good enough. But at the calculus level, we want to do something a little bit more careful and a little bit more precise. And that's where limits come in. So if I get my head out of the way, let's find a nicer definition. A function f mapping from the real numbers to the real numbers, so a real valued function of one real variable, is called continuous at a point c in the real numbers, if and only if each of the following conditions holds true. The first condition tells us, and I'm mixing up my two conditions here already, this is going well for me. The first condition tells us that f of c is defined. The function has to be defined at the point. It has to have a value. The second condition is where the limits come in. The limit as x approaches c of f of x must exist. Then the third and final condition is really the heart of things, tells us that these things not only have to exist and be defined, but have to be the same. The limit as x approaches c of f of x must be equal to f of c. There's a lot to unpack here, and I want to start looking at the conditions. This third condition actually is all we need. If you go into higher level mathematics, you will see the definition of continuity. A function is continuous at a point if and only if this third condition, and that's it. But you'll never find a calculus book that doesn't list all three of these conditions. The reason for that is one of simplicity. Continuity is one of those things that's impossible to prove. But continuity is actually really easy to disprove. So when we're looking at continuity, we're generally looking for which of these three conditions does not hold true. We're looking for places where f of c is not defined. We're looking for places where the limit does not exist. And if we can find one of those things happening, then we're done. But of course, if f of c is not defined, then we don't have a number to put into the equation here. If the limit does not exist, we don't have a number to put into the equation here. And if both of those things fail, well, then we're really in trouble, because does not exist and is not defined, I've stressed previously when we talked about limits, are not the same thing. It's going after two different issues. So, defined, exists, equal. Three separate things to check for. Most of the time we can show something is not continuous by showing that points 1 or 2 fails. If they are both successful, we can check to make sure that they are the same. Before I move onward, I want to point out one other thing. It's the thing right above my head here. This definition tells us about continuity at a point. And continuity at a point honestly doesn't make any sense. Thinking back to that heuristic definition we started with of you can draw the graph without lifting your pen. It's not the same thing, right? Yeah, you can draw a point without lifting your pen. That takes nothing. And so before we can actually do anything with this, I have to extend this definition a little bit further. We can have that f is continuous on some interval, right? The interval from a to b, a subset of the real numbers. And that's going to be true, that's going to be the case if and only if f is continuous at each point c inside that interval. So it's, in a sense, a very natural extension. What does it mean to be continuous on an interval? Well, we take this definition of continuous at a point and we apply that definition at literally every point in the interval. If we can do that, we are continuous on the interval. One more extension. The terminology of continuous that you see at the college algebra pre-calculus level is what we call in calculus continuous everywhere. So to stress, we're not talking about a point, we're not talking about an interval. F is continuous everywhere if and only if f is continuous on all real numbers, the interval from negative infinity to positive infinity. All right. That's a lot of technical detail. And what you're going to find as we go into the first example here is that it's really not anything new. Let's clear out some space here. A classic problem that you may have seen in the college algebra pre-calculus level, whatever courses you've taken previously. Find a value for k such that the function f of x defined piecewise as kx plus 2 if x is less than 4 and 10 if x is greater than or equal to 4 is continuous everywhere. Right. If you have seen this sort of a problem before, it doesn't take any of the construction of limits in order to solve it. That's kind of not the point. The point is that we want to use this problem as a chance to explore limits and explore this definition a little bit more carefully. All right, so the first thing I notice is that the two pieces of this function are very well behaved. Kx plus 2 is a linear polynomial. Well, any polynomial is continuous everywhere. We never have to worry about polynomials, so we don't have to think about that piece. 10 is a constant. Constant functions are continuous everywhere, so we don't have to worry about that piece. The only thing we might possibly have to worry about is the breaking point of the piecewise function. X is 4. So the first thing I think about is what happens at 4. Well, when x is greater than or equal to 4, we use the second piece of the piecewise function. and we get 10. Which means that f of c is defined. All right, that's the first thing we need in order to show that a function is continuous. The second thing we need is the limit. The limit as x approaches 4 of f of x. And because this is a piecewise defined function, that limit will be different on the left and on the right. And since the limit must exist, it will be the case that the limit as x approaches 4 from the left of f of x is equal to the limit as x approaches 4 from the right of f of x. From the left, f of x takes the form of kx plus 2, and from the right, f of x takes the form of 10. These are very simple limits to evaluate. We just plug in for x on the left side. The right side is constant. We don't have anything to do. And we get that 4k plus 2 is equal to 10. Rearranging, solving for k. 4k is 8. K itself is 2. As long as we choose that k is 2, we will have that the limit exists. That's the second thing we need. And the last thing we need is to actually check the value of the limit. Well, we already know on the right-hand side we get 10. On the left-hand side we get 4k plus 2. But now that we've changed this up and we've picked our value of k, the limit as x approaches 4 from the left of f of x, well, if k is 2, it's going to be 2x plus 2. So 2 times 4 plus 2, which is 10, which is the same thing we get on the right. So we can conclude from that that the limit as x approaches 4 of f of x is 10. That's not a 10. That's a 10, which is the same thing as f of 4. All right, so that's all three conditions satisfied as long as k is equal to 2. Once again, the mechanics of going through the limits that I went through here really doesn't add anything to something you may have learned at the college algebra pre-calculus level. Substitute in the point in question and set the two pieces of the piecewise function equal to each other and make sure that everything works out. Now we know a little bit more of why we want everything to work out, and we have some chances to practice playing around with the vocabulary of limits a little bit more. All right. Now that we have at least some familiarity with this definition, let's think back to that original definition again. I want to show you that we can tie this together. That tie takes the form of the intermediate value theorem. Let's let f be a real valued function which is continuous on some interval. Right? So it doesn't have to be continuous everywhere, but it has to be continuous on an interval, and specifically an interval where the endpoints f of a and f of b are not equal to each other. Right? before I get into anything further, this is kind of an odd clause, an odd requirement for a theorem. And it's something that we're going to see a couple of more times in this course. So what I want you to think about is that this is almost always more specific than what we actually know. Generally speaking, when we're going to use the intermediate value theorem, we want to be able to have a function that's continuous everywhere. And then we want to narrow our view. We have a couple of particular points, A and B, where the value of the function is different. So if the function is continuous everywhere, if we narrow our view down to just the points that we care about, the function has to be continuous there as well. All right, thinking about things like that makes it a little bit more obvious why we might care about a situation like this. That's something that very commonly is done in mathematics. For right now, just don't get hung up too much on the requirements. Right? Knowing what we need, in this case continuity, is important, but thinking about why we have such a specific case is a little bit beyond. All right, so the intermediate value theorem, we need a function that's continuous. The rest of it is just minor details. All right. Then, for any k between f of a and f of b, there is a c in the interval from a to b such that f of c is equal to k. And once again, that's a lot. And it's technical and it's overly complicated. So let's try to make it a little bit simpler. Right. The first thing I'm going to say is, without loss of generality, let's assume that f of a is less than f of b. This is another one of those kinds of phrases that show up all the time in mathematics, without loss of generality. In fact, it shows up so often that it usually gets abbreviated and we just say WOOLOG. Without loss of generality, assume that f of a is less than f of b. In the condition of the intermediate value theorem, we only said that they have to not be equal to each other. But not equal to each other is kind of complicated. So I'm looking at a more specific case, and I'm claiming that if we can understand this specific case, we can figure out the other case as well. Because not equal could be f of a is less than f of b. It could also be f of a is greater than f of b. But once I have the less than case established, the greater than case will follow the exact same logic and we don't have to do anything extra. And the reason I want to do this is because the cumbersome part of the intermediate value theorem is, what do I mean for any k between f of a and f of b? Well, I mean that f of a is less than k is less than f of b. All right. Let's now think about this graphically. I have my function. I have points a and b. I have f of a and I have f of b. Because my function is continuous, I have to go from here to there. And if I choose a y value in the middle, my line somewhere has to have crossed over that point. And if you think about making this space between A and B smaller and smaller and smaller, that's where we get that idea of draw the graph without lifting your pen. In order to go from here to there, we have to hit every vertical space in between. And if we take this interval and we take the limit as the interval gets smaller and smaller and smaller, well, then we've run out of horizontal spaces to even worry about. So that's the intermediate value theorem. This is what we use in order to establish that rule of graphing. Another great thing we can do with the intermediate value theorem, if f of a is less than 0 and f of b is greater than 0, pick k equal to 0. Again, this is something that you have used frequently in your life. This is something that computers rely on. If you have ever used a calculator program or a graphing calculator and said, well, I know that there is a root of this function somewhere in this interval, and it asks, or the calculator asks you to choose a point below the root and choose the point after the root, and there must be a root somewhere in the middle. This is a consequence of the intermediate value theorem. A 0 or root must exist. All right. I know it's probably not immediately obvious to you how the intermediate value theorem and the limit definition of continuity relate to each other. And I'll be perfectly honest, it's not immediately obvious to me. I understand how it works. Quite frankly, it took me until I was in graduate school to understand how it worked. So I don't want to try to spend time in this course showing you that these are in fact linked. If the limit definition of continuity is what we mean by continuity, then the intermediate value theorem must be true. I'm asking you to take that on faith so that we don't have to spend an entire week just trying to build up the terminology that we need in order to prove it. Instead, let's stick with what we've been doing, and let's wrap up here with one more problem. So for this problem, I want you to identify all possible discontinuities for this function g of x, which is a piecewise defined function. G of x is x minus 1 over x squared minus 1 if 0 is less than x is less than 2. G of x is x squared minus 1 over 6x if 2 is less than x is less than 5. And g of x is equal to 0 otherwise. Once you have identified all possible discontinuities, then test the function for continuity at those points. I will give you a hint. In this particular circumstance, there are a couple of points that could be discontinuities that are not just the endpoints of the piecewise defined function. So think about all of the things you've learned about continuity in previous coursework. Take a couple of minutes, See what you can do with this one, and I'll see you in the next video.